Capt.S.S.Chaudhari. I'm going to speak about the altitude today. Section to altitude, one taken, goes through various corrections, and those are the corrections we are going to discuss today. When we take the site, the first correction that we apply is index error. Index error depends on the instrument that is a section. Then the next correction is dip. Dip depends on the height of eye. What is the height of eye? Normally, height of eye entered in meters or feet would give dip correction in terms of minutes of hour. Then refraction. Refraction is a tendency to elevate the body. When we look at a star, it appears higher than what is the actual position. So true direction is somewhere lower than the actual apparent direction. Semi-diameter is applied in case of sun and moon, and it depends on whether you have taken lower limb or upper limb. Lower limb is added, upper limb is subtracted. Parallax in altitude is always added. We will see all these corrections along with various horizons in this diagram. So first of all, let us say this is the celestial sphere. If this is the center of the celestial sphere, let me draw the Earth in exaggerated proportion compared to the celestial sphere. On the topmost part, I show you the observer with certain height of eye. If I take a point vertically above the observer, this is observer's zenith, and from observer zenith everywhere 90 degrees off on the celestial sphere, there is a great circle which will be called observer's rational horizon, right? So this is observer's rational horizon. If you consider a small circle whose plane is parallel to the plane of observer's rational horizon but passes through the observer's eye, this would be called sensible horizon. There is yet another horizon. This particular small circle on the surface of Earth limits the observer's vision. He cannot see the water, he cannot see the sea level beyond this small circle on the surface of Earth, and this is the limit of his visible horizon. And seen from the side, let us say this is the direction of observer's visible horizon. Then there is this body over here whose altitude would be taken, and we would be discussing various corrections with respect to the altitude of this body. Actually, if this is moon or sun, we take lower or upper limb, but to understand the basic details, let us say the altitude is taken off the center of the body. So this becomes the observed altitude. Observed altitude can be sextant altitude corrected for index error. Now observed altitude is with respect to visible horizon, but what would be this altitude? This is apparent altitude, and to find out apparent altitude I must subtract something, and this is dip. Dip is the depression of visible horizon below the sensible horizon. As you can see, from observed altitude to get apparent altitude, dip must be always subtracted. So dip is always subtracted. But the altitude has been taken from the surface of the Earth. I need this angle. Assume that the Earth is made up of transparent material and observer is at the center of the Earth, and I need this angle with respect to observer's rational horizon. But this angle, isn't it same as this angle? So I need this angle. So to get this angle, look at this triangle. Look at this triangle. I have apparent altitude. If I add apparent altitude with this, what is this? This is parallax in altitude. Apparent altitude plus parallax in altitude would give this outer angle, and this is nothing but true altitude, because this is the same angle that is measured at the center of the earth with respect to observer's rational horizon. So summarizing a few things, dip is always subtracted, parallax in altitude is always added. If I had initially taken lower limb to get to the center, the semi-diameter would be always added. If I had taken upper limb at the time of observation and to get to the center of the body, upper limb is taken, semi-diameter would be always subtracted. So these are the correction. In addition to these correction, there is yet another important correction, and that is the diffraction. I will be showing it over here. This is the earth. There are various layers of atmosphere. Observer over here. A ray from star would travel to the observer's eye this way, passing through various layers with successive refraction. But observer, when looking at this ray coming to him, would think that the star is over here. So this is the apparent direction and this is the true direction. The angle between them is refraction. As you can see, refraction has tendency to elevate the body, right? So refraction correction is always negative, because refraction would always elevate the body. Refraction is maximum when the body is rising 34.5 minutes negative, and refraction is minimum when the body is crossing your meridian. And if the body had to cross the meridian from your zenith, then refraction correction would be 0. So summarizing these three main correction, dip always negative, parallax always positive, and refraction always negative. Now we'll look at all these correction in a summary form when I make the table. But before I do that, let us discuss the parallax in slight more detail. Parallax is the correction because parallax is an error because you are not observing the body from the correct position. Now from here to here, you are observing the body from here, whereas you should have taken the altitude from here. This is the error in observer's position. Parallax error is caused because there is error in position. So what is parallax? Parallax is the angle subtended at the center of the body by radius of Earth, but through the observer. Every definition has got constituent. If you miss out any one, then the definition goes wrong. Definition means maximum explanation and minimum words. So parallax in altitude is the angle subtended at the center of the body by radius of Earth through the observer. Remember that. So this angle will continue to become smaller and smaller as the body rises in altitude and is maximum when the body is rising. So let us look at all these corrections relatively in a table. Let me place the bodies according to the increasing order from the earth. Say moon coming first, then sun, then you can say planets. Planets I divide in two categories: Venus, Mars, Saturn, Jupiter, and then you have stars. The first correction, index error, depends on the instrument, sextant. So naturally it is applicable for all the heavenly bodies. Dip depends on the height of eye. As I said, the correction is given in almanac. So definitely applicable to all the heavenly bodies. Refraction does not depend on the body. Refraction depends on the altitude. So naturally it will be a correction applied to all the heavenly bodies. They have semi-diameter. Semi-diameter is applied only in case of moon and sun because they project their semi-diameter to us. It is not applied in case of planet and star. Parallax in altitude is applied to the bodies which are closer to Earth compared to the others. So the four bodies, Moon, Sun, Venus and Mars, are the bodies to which Earth projects her semi-diameter, from where the Earth probably appears like a marble, football or a ball. So parallax in altitude, Moon, Sun, Venus and Mars for certain altitudes, and it is not applied for Saturn, Jupiter and the star. So talking about the total correction in the tables, Moon's total correction table would contain refraction, semi-diameter, parallax in altitude. Sun the same, refraction, semi-diameter, parallax in altitude. For the planet, for Venus and Mars, it is refraction and parallax in altitude. In case of Saturn, Jupiter and the stars, the only correction that is placed in total correction table is refraction. Refraction depends not on the body, it depends on the altitude. So if you need to find out refraction correction for any other heavenly body also, you may enter the total correction table of stars.